So here we can think of z and x as random variables, of course. And the graphical model, it comes from this factorization. What I want is actually a joint distribution of x and z. And the natural factorization that I can choose is the joint distribution factorizes as p of z into p of x given z. Why do I call this natural? What is the ordering that I have assumed? That I first sample from the latent space. Once I have sampled from the latent space, then I sample from the visible space, right? And that makes sense. It does make sense, right? For example, if you want to draw these MNIST digits, okay? Now the MNIST digits that you have been dealing with, they have several variations, right? So it matters, first of all, what is the digit that you want to draw, whether it's 0, 1, 2, 3, and so on. So that's a latent variable, right? If you're not given the variables and if you're not given the labels. And for the entire discussion on graphical models, we have assumed that we are not given the labels, right? So what are the latent variables? It could be the digit. It could be the size of the digit, whether you want to draw a small 9 or a big 9. The angle at which you want to draw it, right? Some people write a bit slanted and so on. The intensity with which you want to write it, whether you want to write it as a very bold 9 or a very thin looking 9, and so on. So once you fix these latent variables, then it makes to start talking about the instantiation of that, or what would the visible variables look like. Without fixing these latent variables, it does not make sense to start talking about, okay, I want to produce MNIST digits, right? So that's why even in the case, the other example that we had taken about sunny beaches and mountains and so on, it makes sense that you first decide what kind of image you want to sample, and then you sample from based on that latent decision which you have made, okay? Fine. And what kind of a graphical model is this as compared to RBMs? RBMs were, I'm just hearing some noise, undirected graphical models. And what kind of a graphical model is this? Directed, right? Because you have assumed this dependency from z to x. Okay, you have assumed a direction in the dependency relationship. Okay. Now, given this setup or this graphical model perspective, now we can talk of things that we are interested at inference time. Right? So I have learned this joint distribution, and as usual, the learning part will always come at the end. We'll first assume that we have learned this joint distribution, and now let's see what is it that we are interested in at inference time. So what is it that we are interested in inference time? One of the things that we are interested in is, I give you an x, and you give me the latent representation, right? So in terms of probabilities, can you tell me what is it that I'm interested in? Probability of z given x, right? This is what I'm interested in, and I can write it as this. Okay, whatever you see on the right hand side. Is there a problem with this? Of course, assume you have learned the parameters. Is there a problem with this? Which term is a problem here? P of the denominator. The denominator is again this massive integral, right? So the denominator is nothing but this integral of the numerator, right? And here's where I had this. So this integral in turn is an integral over many variables, right? So it's z1 to zn. So this is again intractable, and we come back to the same situation that we are interested in computing some quantity, but that requires this expectation, and that expectation is intractable because you have a large number of variables, okay? In RBMs, how did we get rid of this expectation? By doing Gibbs sampling, right? So that's one way of tracking it, or rather sidestepping it. In variational autoencoders, we're going to do something different. We're going to cast this into an optimization problem and then try to learn the parameters of that optimization problem, right? So that's a different way of approaching this problem. Both RBMs and variational autoencoders deal with the same problem, that you have this intractable expectation or integral, but there are different ways of dealing with it, okay? So in VAs, what we do is, we assume that instead of pz given x, which is the actual thing that we should have computed, and it is intractable, the posterior distribution that we are interested in is some q theta z given x. This is what I'm going to assume, right? So I'm saying that I don't know what pz given x is, I can't even compute it, but I'm saying that there is another qz given x which has parameters theta, and now I'm going to set up an optimization problem. What should be the goal of that optimization problem? What are the parameters of that optimization problem? Theta. Okay, that's one thing is clear. What should be the objective function? we are dealing with two distributions. I know there's a two distribution which I can't compute. I am proposing an arbitrary distribution with some parameters. What is it that I would expect from this distribution? It should be as close. And how do you say this in mathematical terms? I would want to minimize the KL divergence between these two distributions. Okay. Now the first thing I'm going to do is, again I'm going to assume a family for Q. I'm going to assume that Q comes from a Gaussian family or a normal distribution, and the parameters are mu and sigma, and these parameters in themselves are expressed as some other parameters, right? As a function of some other parameters and a function of the input, of course, because this is the given quantity. Same thing as what we saw in the neural network perspective, nothing different here. And now the parameters of the distribution are expressed in terms of parameters of some other function, and our job is now to learn these secondary parameters, right? Okay. And again we'll eventually reach the same destination, that these parameters are going to be the parameters of some neural network. Okay. But in an abstract way, this is what I'm going to write it as, right? So what I've done is, I couldn't compute P. I have proposed a Q which has certain parameters. These parameters I'm going to express as function of some other parameters. I'm going to set up an objective function or an optimization problem, and the optimization problem is going to be with this set of secondary parameters. Okay, fine. And now what's the objective function? KL divergence, right? So the KL divergence between the proposed distribution, which is Q theta, and the two distribution, which is P. Okay, this is what I want to minimize. And what are the parameters of the objective function? Everyone, theta, right? So there are parameters of the neural network, and we'll come back to this. Okay, so now first what we'll do is, I've just rewritten this KL divergence, and this KL I'm just going to call it as D. It just stands for divergence, right? So we are going to work with this KL divergence and try to expand on it. Let's just see what it looks like. Okay. So what's the formula for KL divergence? It's not, is it symmetric, asymmetric? Asymmetric. Okay, so that's good. So the order in which you tell me matters, right? So it's dash log dash minus dash log dash. So, and of course integral. Okay, now I'm also confused. No, it's not that. So it's q log q minus q log p. Okay, and the integral, again this integral is intractable. Whenever we have an integral, what do we replace it by? What do we replace it by? Summation. Expectation, right? We just write it as an expectation. So we can write this as, so inside the expectation I have these two quantities, just so that you understand. And outside I have just written it as an expectation with respect to this distribution, which is exactly the first term in both these integrals. Is this conversion from the integral to the expectation clear? Right? Everyone is fine with that? Why do I see blank faces? Okay. And now since this is a bit tedious to write, I'm just going to use a shorthand Q for this. Okay. So this entire quantity, whenever you see capital Q in the expectation, it means Z coming from the distribution Q theta of Z given X. So just saying it itself is tedious. Okay. So, and so that's what I'm going to do for this guy. And now the second thing I'm going to do is, I'm going to write P of Z given X as the standard thing. I'll just write it as the base rule. Okay. So now what will happen inside? What will be the terms that I'll get inside? Of course this term will remain as it is because I'm not touching it. What about this term? Log of minus log P of X given Z. Everyone please, I'm assuming it's too easy, that's why you're just offended that I'm asking you to do this. Okay. So that's what will happen, right? So this term will get replaced by these two terms. So the two numerators and the one denominator, right? And the signs are getting adjusted accordingly. Okay. So, okay, I had two terms to deal with, now I have four terms to deal with. Now, one of these terms, it looks like I can take it out of the expectation. Which one? Which is the term which I can take out of the expectation? And this is not a simple question, so I'll wait for everyone to answer. The expectation is with respect to which random variable? Z. So which of these terms can I take out of the expectation? Log of P of X, right? So that's the one which I'm going to take out. Okay. And I have this quantity, I have this quantity and this quantity. Okay. What's the first quantity? Yeah, he knows why I did that. It's this, what I meant is this looks very similar to this, and which was actually derived from here. So now can you tell me what it is? KL divergence between QZ given X and P of Z. Okay? The second term I'll leave it as it is, and the third term also I'll leave it as it is. Okay? And now I'll just rearrange some things. I'll keep log P of X on one side. Why? Because what's the recipe? Maximize the, so that's the term which I care about. I'll keep it on one side. Okay? And then I have this blue term, and then I have this red term. Okay? If I take the red term on the other side, what will I get? The place where we left off when we are doing the neural network perspective, right? So we had said that we want to maximize the log likelihood of the data and minimize the KL divergence. Oops. Okay, it doesn't matter. We can anyways continue. So we have this log of Px on one side, and we have these two terms on the other side. Okay. Now, what is the red term actually? This was the starting point, right? This is the quantity which I said we want to minimize. I said that there is a true distribution, there is a proposed distribution parameterized by theta, and I want to minimize the difference between these two. Okay? That's what my starting point was. The other way to look at it is that, and now what's the property of KL divergence? It's always greater than 0, less than 0, greater than equal to 0, less than equal to 0. What is it? Greater than equal to 0. Okay? So now, this is the quantity that I care about. Okay? Let me just call this as A, and let me just call this as B. So the quantity that I care about, let me just call it as C, is actually A plus B. And B is, okay? So what can I tell about the relation between A and C? There are many things you can say about it. I want in terms of greater than, less than, equal to. C is greater than or equal to A, right? Or rather, A is less than or equal to C, just to give a different answer. So what does that mean actually in terms of lower bounds, upper bounds, and so on? Remember, this is the quantity that I want to maximize. Now I have another quantity which I know is always less than or equal to this quantity. Or rather, I know that this quantity is always greater than or equal to that quantity. Now think of it this way. I want to maximize C. I know I cannot maximize C. Why? Because it's computing it is intractable, right? You have this integral over integral and so on. I cannot compute that. But I have this another quantity which I know that C is always going to be greater than that quantity. So if I take this other quantity and I keep maximizing it, what would happen to C? It will also get maximized. Do you get that? Everyone gets this? So instead of maximizing C, what can I maximize? A. Does that make sense? Okay. Why do this? God knows, but at least by the premise, right? You can do this. Okay. So we are interested in maximizing the log likelihood of the data, and we have this relation that the log likelihood of the data, oh, this is wrong. Why do I always make mistakes on the most crucial point? Oh, no, this is correct. No, this is correct. Sorry. Okay. Okay, the red term is just gone. I thought the red term became blue or something like that. Okay, this is fine. So this is again the same thing, C and A. So I can't deal with C. So the quantity on the left hand side is actually a lower bound for the quantity on the right hand side. So if I can't deal with this guy, let me just deal with the lower bound. If I can maximize the lower bound, it's the same as maximizing this guy. Is that clear? Okay. So that's what I'm going to do. I'm now going to come up with an equivalent objective function, which is to maximize this blue term that we had. Okay. And the blue term has one KL divergence and another expectation term. So I still need to tell you whether this is any easier to deal with. what are the parameters of this distribution or this, what are the parameters of this objective function, I still need to tell you all these things, right? But for now, we have arrived at a certain objective function starting from, I would say, legitimate and reasonable and well thought of, well principled steps, right? We have not done any random things anywhere. We have just started with what we would like to do and gave a justification for doing that is equivalent to doing this, okay? Fine. So this quantity, right? There is nothing unique to variational autoencoders. This is used in a lot of graphical models. This is known as the evidence lower bound because it gives you a lower bound on the probability of the evidence that you're seeing, okay? And this method of optimizing this blue term instead of the term that you actually care about, which is log p of x, is known as variational inference. And hence, these autoencoders that we are looking at are known as, please show some enthusiasm, variational autoencoders, okay? Of course, the question is, why is this any easier than working with the original objective function, right? And this would be easier because of certain assumptions that we are going to make. When you're working with graphical models, just deal with assumptions and approximations. Don't cringe every time I use the word assumption and approximation, okay? Fine. So first, let us just reintroduce all the parameters, right? So this was our objective function, and now we have reintroduced the parameters. So q was parameterized by theta, and p of x given z was parameterized by phi. Nothing new here. This is the same that we had introduced even in the neural network perspective. So I'm back. I'm trying to kind of now merge the two. So from the neural network perspective, I had reached a certain objective function. You can go back and check that we have reached an equivalent objective function starting from the graphical model perspective. And now the only job left is, one is that this optimization function is with theta phi. We need to add this, okay? And the other thing is to show that this is tractable. Fine. So now let's get into training. So at training time, we are interested in learning the parameters of theta and phi, which maximize the above for every training example given to us, right? For each of the xi's, we are interested in maximizing this quantity, okay? So that total objective function is just going to be sum over all these individual objective functions. Is that fine? Okay. But now my favorite algorithm is stochastic gradient descent. So what do I do in stochastic gradient descent? What's my loss function there? One of the terms in the summation, right? So stochastic gradient descent, I just have one training example. I compute the loss for that and just backpropagate. And that's just the same as saying that I'm going to deal with only one of these terms in the summation at any given point of time. Is that okay? Fine? Okay. So, and of course, we'll shorthand this just a side note. So we're going to assume that we're using stochastic gradient descent. That means at any point, I just need to deal with one of the terms in the summation. So my effective objective function is going to be just one of the terms. I've basically got rid of the summation, and I just have this one term that I need to focus on, okay? Now, first, now you have given me this example xi. I should first be able to compute the loss. If I'm able to compute the loss, backpropagation is not my problem, right? That I can do, okay? So first, let me try to compute the loss. So let's look at this term first. So we'll be looking at that term. But before that, the moment you give me a sample xi, what am I going to do? I'm going to pass it through the encoder and compute what? Mu x and sigma x. Is there something wrong here? Let's assume sigma also. Is there something wrong here? Was I interested in the means of z or x? What does the encoder predict? P of z given x, the parameters of p of z given x. Why have I written as mu of x? It's a function of x. So please don't get confused there. It is not the mean of x. I'm just saying that the correct way of noting this would have been mu z, which is a function of x, right? So mu z of x. But that's too cumbersome and it will become hard to read as we go ahead. So remember that when I say mu of x, I just mean that compute the mean of z given x, which is a function of x. Is everyone clear with this notation? If you're not, you'll get totally lost for the rest of your life. Okay, is that clear? Okay, so that's what I mean. Mu is a function of x, and mu is actually a parameter of the distribution z given x. So the moment I give you x, with whatever is your current configuration of the parameters, this is a simple feed-forward neural network. You can give me mu and sigma. Okay. Now, I can do this. So now the second term here was actually the KL divergence between these two distributions. What was this distribution? The second one, P of Z. What did we assume? Standard normal distribution. Okay. So the second term is actually the KL divergence between two normal distributions, one being this and the other being this. Do you guys know a formula for the KL divergence between two normal distributions? I want everyone to say yes. Why do you know that? Or you all did it in the assignment? Okay. So I hope this is the formula that you arrived at. If not, then you can be sad after the lecture is over, but right now please focus. Is that fine? Okay. So the difference between two normal distributions can be computed as a closed form, and in particular if one of the distributions happens to be 0i, this is the answer that you get. Is this quantity easy to compute? What is this quantity? Is it a scalar, a vector, a matrix, a tensor? Scalar. Is it easy to compute? Okay, let's look at each of these terms. Okay. You're looking at the trace of sigma x. Straightforward. You're looking at the dot product between two vectors. I'll not tell you what k is, although it's written on the slide. And then you're looking at the determinant. So all of this is straightforward to compute. Okay. So at least one term of the objective function is easy to compute. At least that much we have achieved by transforming all that circus and coming to this new objective function, right? So at least I've shown you that one term is very easy to compute. And k is nothing but the dimensionality of the latent variables, the number of latent variables that you have, right? And that's, I hope this is the closed form solution that you came up with in your assignment. Okay, is that fine? So given an x, I can compute mu and sigma, plug mu and sigma into this formula, and I'm done. I've computed the second term of the loss function. Everyone is fine with this? Okay. Now this is the second part is what you're not going to be fine with, but what can I do? So this term can be computed easily once you have done the forward pass. Now let's look at the other term in the objective function. Any guess what I'm going to do? This term is supposed to be computed. Okay, so this was not this, sorry. We already have one nasty integral there, we don't need the other summation, right? This was summation over all the data points, but we don't need that, right? Because we're just dealing with one data point. So this is the expectation with respect to Q, the distribution Q. How am I going to compute this? This is as bad as anything, right? This is again some nasty integral is going to come into play. So I've again forgotten what's there on the next bullet. Is this what you all expected? This expectation has to be computed over all possible values of z. I'm going to replace the expectation by a point estimate. Something similar we did in RBMs, hence I had that slide which said these are the characteristics of RBMs. Right? So almost you can see that we are coming back to similar assumptions but using them in very different contexts. Right? So I'm going to replace this entire expectation using a single z drawn from the distribution n mu comma sigma, and I've already computed mu comma sigma in the forward pass. Is that fine? So I've computed mu comma sigma, I'm going to sample a z from there, and I'm just going to estimate this expectation using this single point estimate. Is that fine? Hence computing the first term is also very easy. And of course it is. I mean, we did a nasty approximation, but we'll just live with it. Just because that's going to be a part of the game. Once you're dealing with graphical models which have a large number of variables, you'll have to do some kind of an approximation or an assumption. So here we are making this approximation, which is a point estimate. Okay. So that was one thing. The second is, as usual, we are going to assume some parametric or some family for P of x given z. And again in variational autoencoders, we are going to assume that P of x given z is actually a normal distribution. So if that's the case, what does this term actually boil down to? So why am I computing this? Because I'm going to replace this by one single value, right? And that single value is nothing but log of P of x equal to xi, which was my input, given the z which I have sampled from the distribution. So this is one quantity which I need to compute. Now in the case of a normal distribution, what does it boil down to? You can answer it even though the answer is there. It's log of e raised to minus something. So log and e will cancel out. What's that minus something? Xi minus mu. Now this I'm calling it as mu z. What does that mean? It's the mean of the distribution x given z, which is a function of z, and that's what the decoder is going to compute. Okay, and this is what that 1 point estimate boils down to. How many of you get this? Please raise your hands. Not many. So I'll just write it as some 1 by some constant e raised to minus xi minus mu z the whole square, and oh no, sorry, I can just do it in one variable case, right? So you have the sigma square, and we had assumed that this is unit variance, so this is 1. It should be 2 sigma square. Okay. So what is this? This gives me the probability of x equal to xi. That's what the normal distribution gives you. How many of you are completely lost at this point? All I've done is written the normal distribution. Is that such a crime? Oh, I see why you are lost. Okay. How many of you still don't get this? So for the normal distribution, okay, let's think about the univariate case. P of x equal to xi is given by 1 by square root of 2 pi sigma. Can anyone help me with this? E raised to minus xi minus mu of whatever, mu whole square divided by 2 sigma square. The same formula you can imagine it in a multivariate case also. You should not imagine, you should know it, but if you don't know it, just imagine it. Okay? Fine? Now, in fact, should I just work with the univariate case? Okay, not. What I assumed about the variance? Unit variance, right? So this goes off. Okay? So this is P of x equal to xi. Now if I take the log of this, what will I get? Log of 1 by square root of 2 pi plus log of e raised to this. The log and the e will cancel, and you will be left with xi minus mu the whole square. Okay? By 2. This term I am calling it as a constant, and this exactly is the same as this, except that it's in the multivariate case. Now everyone gets this? So if you have a Gaussian distribution, the log of the Gaussian distribution or the log of the probability is just going to be the squared error difference between your observation and the mean of the distribution. Everyone gets this? Okay? Is this term easy to compute? Do you know xi? Can you compute the second term? How will you compute this? You have sampled a z. You just pass it through the decoder. The decoder will give you mu of x given z as a function of z, and you just take the difference. So you're just taking whatever the decoder predicts, that's your mu. You're taking the difference from the input and just taking the square difference. Everyone gets that? How many of you don't get this? Some people started raising their hands. How many of you get this? Okay, good. So the first term, so now we have the full loss function, right? So this is what we got from the KL divergence term. Oh no, not this, this whole thing. And this second term is what we had from that nasty first expectation, which we approximated by a point estimate, and the point estimate just happened to be this value here. Okay? So now we have this full loss function, which we know is computable. Of course it is. And now what do we do? Go home. Now what next? You have the loss function. You have the data. You have the, by now you should memorize the sequence, right? Data, model, parameters, objective function. What's missing? What's the algorithm? Sorry? Stochastic gradient descent. Back propagation. What's the problem with using back propagation here? Can you use back propagation here? Can we do back propagation here? Okay, let's, in fact, we just said we know the data, we know the model, we know the parameters, we know the objective function. Write down the model. Write down the output as a function of the input. Can you do that? Can you write the output as a continuous function of the input? Why no? or we have this sampling step. You cannot write it down as a deterministic function of the input. Right? The sampling brings in this randomness, which brings in this discontinuity. The moment you have a discontinuity, what can you not compute? The gradients. If you cannot compute gradients, gradient descent is off, backpropagation is off, right? So that's still one problem that we need to solve. We have solved the problem of the loss function, but we still don't know a training algorithm. Okay. So the loss function can be easily computed, and the objective function, the optimization problem is with respect to theta and phi. There's a catch. The catch is that you're using this sampling. You're sampling from the distribution mu comma sigma for the variable z, and that brings in this discontinuity. And because of that, you cannot have the output as a continuous function of the input. Now, VAs use a neat trick to get around this problem, and this trick is called the reparameterization trick, wherein what we do is we move the process of sampling to an input layer. Without me telling you anything else, and assume that I give you a method of achieving this English sentence. What does it actually mean? So here's a hint, right? We cannot get around the sampling. That was the whole premise of designing variational autoencoders, that we want to sample, we don't want a determinist function. But we want the sampling to happen at a stage so that it does not affect our path. We should still be able to get an end-to-end path from the input to output. Is that wish list okay? Is that objective make sense? Do sampling for all I care, but just stay off my path, right? Just don't come in the path from the input to the output. So in that context, can you read this sentence and try to see what would happen? It's not very obvious, but I just want you to think about it so that at least it opens up something in your brain, and when I give you the solution, at least maybe you'll be able to relate to it, right? Anyways, we have time, so it doesn't matter about it, right? So let's see what I mean by that, right? So before I get into the trick, let me just tell you something about normal distributions, right? I mean, nothing profound, all of you know this, but suppose you have one normal distribution which has parameters mu and sigma, and another normal distribution which is the standard normal distribution and has parameters 0, 1, okay? Now, what I could do is, if I want to sample from the distribution mu, sigma, what I could do is I could sample from the distribution 0, 1, because that's easier. I can easily find a library which can do that. And once I sample from that distribution, all I need to do is move the mean and adjust for the variance, right? So this term, because it's addition, it makes sure that I move the mean, and this term, since it's multiplicative, it makes sure that I adjust for the variance. Does that make sense? Right? So instead of variance 1, now the variance becomes sigma, and instead of the mean 0, I have shifted it by mu. This is a standard trick which probably you have done in some of the courses that you have taken, right? If not, at least for now, just mug it up and go back and look it up later on. But what it means is that instead of drawing from mu sigma, I can draw from 0, 1, and then just use the mu and sigma to adjust it. Now, based on this intuition, can you rethink about what can be done? I have computed mu and sigma. I don't want to sample from mu and sigma, because if I do that, mu and sigma depend on some parameters. The moment I sample from something which depends on parameters, my chain breaks. So I don't want to sample from n mu, sigma. Again, I don't expect you to immediately arrive at the solution, but do think about it, right? And this thinking is what is important. The solution is, of course, there on the slide. That's why we have 3 more slides. Okay, so let's see. So what I'm going to do is, I'm going to take the x, I'm going to compute mu and sigma. Till this point, everything is deterministic. There's no problem, okay? Now, I'm not going to sample from the distribution mu and sigma. What I'm going to do is, I'm assuming that I have another input, which is epsilon, okay? I'm going to sample from that. So I can think of it that I had the input x. In addition, I had an input epsilon, which came from a normal distribution, right? And now, whatever mu and sigma I have drawn, I will just add, I'll just do this operation, right? This is exactly what I'm doing. I'm multiplying the epsilon by the variance, and I'm adding the mu, and I'm getting a different quantity. Okay? Now, in terms of the parameters of the network, it is a deterministic, is it a deterministic function of the input? I've pushed all the randomness to epsilon, right? Do you get that? How many of you get this? Please raise your hands. If you don't, can you write the model equation now and see if you can write it as an end-to-end function of the input, the output as an end-to-end function of the input, where your input now is x plus some epsilon. I don't care about what happens here because I'm not going to backpropagate anything to the epsilon. I don't care about that. I only care about these paths remaining clean. Does everyone get this? Can I move on? Please raise your hands if you get this. Okay. So with that, we are done with the process of training variational autoencoders. We have described the data, the model, the parameters, the objective function, and the learning algorithm. And here's the model. I have mu and sigma, which are functions of x parameterized by theta. There is no randomness here. The randomness has been moved to epsilon, right? So still in terms of the input, my output is a deterministic function of the input, and the randomness has gone to epsilon. Everyone sees this now. This is very, very crucial. This is one of the neatest tricks, so please make sure that you understand this. Otherwise, there is no point in variational autoencoders because without this trick, you cannot train them. So it's very important that you understand this. Everyone fine with this? Okay. So now you can write everything. Once you can write the model, that means the output as an end-to-end function of the input, then you're done. Right? Now you can backpropagate. So now everything falls into place. Now what happens at test time? What do we need to do at test time? What are the two things that we're interested in? Abstraction and generation. Remember, when we started this lecture, I said that in an autoencoder, you take an x and you reconstruct an x. What's the fun in this? Like, where's the magic trick here? Right? You took an x, you just got an x back. So where's the magic here? There's no magic here. Okay? So we'll get to that answer now. But once you have trained the model, once you have done all this epic saga, what do we want to do now? We want to either use this model for abstraction or we want to do for generation, right? So let's look at the abstraction first. What does abstraction mean? That I'll give you an input and you will compute a hidden representation. That means I'll give you an x and you're going to compute the z. So which part of the network is going to kick in? Encoder, decoder, both, nothing? Everyone? 630, but everyone? Encoder. Okay, good. So first for abstraction, I'll give you x. What will the encoder predict? It will give me a z, right? The output of the encoder is going to be a z, right? I give it an x, the output of the encoder is going to be a z. What does the encoder give me? Mu and sigma. It gives me a parameters of the distribution z given x. It does not give me z. What do I want in abstraction? Z. So now there is this gap, right? The encoder is not capable of giving me my z. What will I do? I will sample from that, right? So the encoder will give me mu and sigma. I'll sample from that and I'll get a z. So now unlike an autoencoder, which for a given x always gives me the same z, what will happen in a variational autoencoder? I could get different z's, right? Each time I sample, I should get a different z. Of course, in proportional to the parameters of the distribution, but I'll still get this different z's. It's no longer deterministic, okay? And how you sample is up to you. You could either sample from the distribution mu comma sigma, or you could again use the same parameterization trick. You could sample from the distribution 0 comma I, and then do this shift of variance and shift of mean, right? But the bottom line is the encoder does not produce a z, it produces a distribution, or rather it produces the parameters of a distribution, and then you can sample from that distribution. Okay, so that's what this slide essentially says. So the question is that mu and sigma were trained in a way that they become close to 0 comma I, right? That means my latent distributions, my latent variables come from the distribution 0 comma I. So why can't I just sample from that distribution? Why do I even need to feed an x? I don't even care about the x. I just sample from the normal distribution and say this is the abstract representation. So I'm going to give you an answer, and then I'm going to contradict that answer when I talk about generation. And that's what happens in optimization problems. There's always this trade-off, right? So that's our objective, that the KL divergence will be minimized. Will it actually collapse to 0 comma I for all the x's? That's not clear, right? So what will happen in practice is you learn these distributions. which are all mean shifted and variance shifted, because you have not been able to drive the mean to 0 or the variance to unity, right? It will still, the means would still be different for these x's. They'll be as close to the normal distribution as possible, but still slightly different. That's why you need to feed in this x to get that particular distribution and sample from there. Okay? Now I'm going to contradict this story when I talk about generation. But everyone gets this? Okay? Fine. So now for generation, what are we interested in doing? Given x, reconstruct the x. That's what generation is, right? I take an image, regenerate it and give it back to you, right? And pass it through my GPUs. We'll have many of those and then give it back to you. What's the generation problem? From thin air, right? I'll give you a z and you have to give me back an x. How do we do this generation? Autoencoders could not do this because we did not know what z to give it. Now what will we do? Sample from where? Sample from which distribution? Standard normal distribution. Why? Why do we sample from the standard normal distribution? What kind of z's were we interested in? Ones which were likely given x, right? Those were the kinds of z's that we were interested in. Not any z from that entire large high dimensional space. We were interested in z's given x. What did the training ensure? The distribution of z given x goes close to the standard normal distribution. So now, and that's where my contradiction is, right? Now at test time, if I draw from the standard normal distribution, I know it's as close to some of the z's that I had set during training. Does that make sense? What I had done during training is I had made sure that the distribution z comma z given x goes as close to the standard normal distribution as possible. The answer which I gave to her is I said that it's close but not very close, but I can still deal with it. It's still going to be close to the standard normal distribution. So now if I sample from it, it's much better than sampling in the blind from the entire high dimensional space. It's still closer to the distributions that I've learned. All of them are closer to this standard normal distribution. Hence, if I draw from this distribution, I am feeding the decoder something that it can deal with, because it comes from a distribution that it had seen during training time. Does that make sense? How many of you understand that? Please raise your hands. Okay, good. So that's what I'm going to do. At test time, I'm going to draw from the distribution 0, I. The decoder will take this and it will predict the mean, and then I'm going to sample an x from this mean. So again, the decoder is not deterministic. It does not take a z and give me a fixed x. From the same latent variable, I can generate multiple images. Multiple sunny beaches with white sand and no people, right? I could have multiple images with the same latent configuration. Does that make sense? So that's what I'll do at the time of generation, and the rest of the slide just explains why this works, because we have trained it to be close to the standard normal distribution. Okay? Fine. So think about these. These two questions are important, right? So on one hand, her question that if it's all become standard normal distribution, why either bother about feeding it an x? You could just say that don't show me your x. Here's a latent distribution which comes, latent representation which comes from the standard normal distribution. It's fine, right? But the answer to that which I gave was that it's not going to collapse on the standard normal distribution. It's just going to be close to it, and it will be differently close to it depending on the value of x. Hence, you need to compute the mu and sigma given the x, right? But however, at the time of generation, I am saying that all of these are close to each other. So as an approximation, just draw from the standard normal distribution, right? So this, I'm just doing a trade-off between the goals at abstraction and generation. Okay, is that fine? Okay. Someone actually showed me a thumbs up. Okay, good. For first time. Okay, so we are done with variational autoencoders. Now we have 3 more lectures, Tuesday, Wednesday and Thursday. Thursday 8 o'clock. We have a lecture on Thursday, right? Yeah. So anyways, I think I need 1 lecture for autoregressive models and then 1 lecture for GANs, and perhaps 15 minutes to bring this entire generative modeling story to an end, right? Like, so we started with RBMs, VAs, autoregressive models and GANs. what are the similarities, differences between them, and what are the limitations or advantages of one over the other, right? So we already hinted at something that VAs in the end try to make similar kind of assumptions that we made for RBMs, not exactly the same, but in the same taste and so on, right? So we'll try to close that. Hopefully I should be done in 2 lectures. If not, I'll take the lecture on Thursday also, okay? Thank you.